Yeah, thank you very much. Thanks everyone for having me here. This should be a lot of fun. It's it's too bad it can't be in person. I'm just closing some stuff in the background here. Okay. So I'm going to talk to you about electromagnetic fault injection on practical devices. So what really that means is we're going to look at electromagnetic fault injection and how it can work for actually working with, like, if you want to look at where does this work in real life, not just on theory. What are some examples of that? I'm going to work through some examples I've done this on. And I'm trying to use things that I've sort of documented at least a little bit, some of them fairly well, so you can actually dig into a lot more detail. So this talk is going to be, a pretty quick high-level overview of it, but hopefully it gives you some sort of ideas for how you can play with fault injection in general and electromagnetic specifically. Okay, let's get that. So I'm here, by the way, so we're all, or I don't know if everyone there is remote, but at least I assume the majority are. I'm on the East Coast of Canada. So there's, not a ton of tech around here, but it's sort of a nice place to live. It looks something like that until recently. It's starting to get a bit into winter now. Over here, what I'm doing is I've been working on this open source project, ChipWhisperer. I've been involved in academia for a while. This is kind of how ChipWhisperer spun out. So I'm still involved in that right now at Dalhousie, the local university, as well as trying to develop tools and stuff like that to support the whole open source ecosystem. And actually, so I, normally it would be really nice to be in Torino itself. I've been close to there before. So for people in Italy, I probably recognize Ivrea. So there was a few months I lived in Rocca Priora. So I've been up that way at least. So you can imagine this photo smells very good for anyone who hasn't been to this giant orange fight that happens in Ivrea. I assume, I don't know if it happened this year, but I think it's still going on generally pre-COVID times. All right, so back, from that on to the tech stuff. So really quickly, fault injection, if you haven't seen it before, what is it, right? So fault injection is some way that we can bypass security. We can accomplish interesting things effectively on embedded systems. And why this works so well is that if you imagine a embedded system like this that has like an image. So, say it's a whatever car ECU trying to boot an image. And so we have this pointer to the image and you need to check, okay, should I actually boot this image? So you have some function call like this and it says signature okay image, right? Equals fail. So if that fails, then it just goes into this infinite loop, right? And then the rest of it loads the image here. So what fault injection is trying to do is actually bypass this, or either, so in this case, what fault injection could do, right, is this loop. If you were to jump out of it, it's actually going to execute the rest of this. And let's actually show you. I don't have this on a slide, but let's just do a little demo here. So what I'm going to do, just clean up this slide a bit. Okay, so this is pretty fun if you're kind of interested in this stuff. There's this compiler explorer website that you might already know about. But let's say, how does that code actually achieve a fault injection, right? So if I put some code here, right? So if I say, if signature okay image equals 0, right? And let's just make our image. So I'm just going to put some sort of garbage code that was just like on the slides though, right? We go into an infinite loop. Otherwise we call do boot. And let's see if it's going to complain that. So it's complaining because I didn't define these. So I think it'll just make external references if we do this. And so what I kind of want to show you here, so this is going to be some ARM assembly code. Oops. Image. We're doing live debugging here, makes it more interesting. Okay. So that should work. Oh, this needs to return int. There we go. So there's our code. So what was I trying to show you with this, all this stuff? Can make this bigger. This is as big as it gets, sorry. So you can try this yourself. So you can go to those websites, you can throw in some code, and what you'll see is that there's basically a compare operation here, right? And if you look at how it's generating this code, it's put a branch right here. So there's a branch that's just sitting in this loop that's jumping to L3, right? And this is exactly the same. So if you were here and you suddenly go here, the code executes as if that comparison passed, right? So there's no super fancy attack here needed. And this might not be such an obvious one, right? If you just call like exit or something like that, it's not defined here. That might just spin into a while loop. So that's the kind of interesting thing with fault injection, is that it can be very powerful. So in this case, we didn't need to worry about the image. We didn't need to worry about breaking the encryption, anything like that. We just kind of skip past that while loop. And you can see it's going to be pretty easy because it's just like a loop that if it jumps out of that loop, so if it doesn't execute the branch, then it's all over. There's more complex stuff we can do, but that's kind of the basic idea. And to do this, what I'm going to do is I'm going to use a strong magnetic field. So we're going to do this with something called electromagnetic fault injection. So there's a few ways of injecting faults. I'll show you a few after here too as well. But the basic idea of this way is that we have a coil, you pass a strong pulse through the coil, and if I have a target chip here, right, let's just draw a chip. This magnetic field is going to induce voltages onto the die itself, and these voltages are going to affect nodes and things like that on the chip. So it's a pretty simple idea, but it actually works pretty well in practice, right? And so when I say a coil, it's something like this. So these ferrites, right, you can get, and then you can just wrap a few turns of coil around it. These are even like off the shelf, right, inductors designed for use in electronics projects. But something like that actually works pretty well as an example coil. So there's quite a few examples out there. The end goal is you want to drive a bunch of current through this coil to generate a strong pulse. You can do pretty similar things with like a piezo lighter. So I played around with these before for just, doing really simple demos, but then someone's actually shown, so there's a nice blog post showing using these on an Android phone. So this is not, just because it's a cheap tool doesn't necessarily mean it's actually, not useful in real life. And it really comes back down to this kind of idea that when things fail, you go into this safe state is pretty common. Or if things fail, it goes into a bootloader backup mode, right? So there's a lot of devices that all you need to do is have them fail, not at a super specific time. And for things like that, these low-cost, super low-cost tools will work. And you can obviously build this up a little more if you want. There's some open source designs out there for EMFI tools. So what we also have is there's devices like this. So this was from a presentation. And basically what you do is you have a voltage supply, right? So a high voltage supply. This is then discharged. So this would be like you'd have some capacitors here. You have an electronic switch that's then basically really quickly closing that supply to generate a strong pulse. So here they use a capacitor just to safely couple this into the inductor. So this is kind of a low-cost architecture that's actually fairly safe. And I say fairly safe because it does not have high voltages here all the time because of this capacitor. So this is really important. There's other designs you see basically that don't have this capacitor here and put a switch at the bottom side. And the problem here is you always have the high voltage on that probe that you're touching. So if you have, your device, you don't want this to be at high voltage all the time, which some designs will do. And it's just obviously not great if you're going to be handling it a fair amount. So it does work though. I mean, if you have the safety mechanisms in place. So the first open source EMFI tool, BadFet, kind of used this method of having a slightly more dangerous because you had a lot more flexibility with voltages, with pulse shape and stuff like that. So there is variations out there, right? So I'm going to use my own design that is a much more expensive tool that we sort of sold commercial or sell commercially. And it basically uses a method where you put some of the electronics at the what they call high side drive. So it's a much more complicated way of generating the pulse. It sort of lets you still be safe. So I can, if I take this device here and I charge it, so then it's generating the high voltage, you can touch that freely and you can touch it during discharge and it's not going to shock me. So that's kind of the idea of that. Okay. So the first example I'm going to give you, this was one of the first things I looked at with using EMFI on sort of a more real device, was this Bitcoin wallet. So these Bitcoin wallets, the quick summary, right, is that you had this hardware wallet that's trying to protect your private key. And what was interesting is that they give you a recovery seed, right? So the recovery seed is like, you write this down, and if you lose this physical wallet, you have a way of getting everything back. Right. So the recovery seed is your private key, just written in a different format effectively. So it warns you, right, that if someone has this, you can get everything associated with it. You don't need any other data but that recovery seed. You enter that seed into the new Trezor device. And this recovers your private key. And then it's like you have a direct copy. So it's like you have a clone of your old device that you assume the old device is dead. So at the time, when I was looking at this, so this is changed a bit now, right? You could password protect it, but it sort of wasn't, I think maybe as encouraged. Like it was encouraged, but a lot of people didn't do it because there wasn't a clear threat model where someone could get this recovery seed out, assuming they had physical access to your device. So if you password protected the seed, what it means is that seed is not enough, right? You now need a combination of that seed and your password to recover from the data. So anyone who used a password was fine with that. And why this was interesting is if you look inside the Trezor, there's basically this microcontroller here, right? And this microcontroller is kind of like right underneath the case. So you had a microcontroller, you had the plastic case. And this makes it really interesting for EMFI because if we can sort of attack this device, we know the microcontroller is in this region, right? If we can attack this device, we could do that without physically opening it up. So even if someone put security seals all over the device and, re-encapsulated it or something like that, or was just inspecting it carefully, potentially we could look for an attack that could work without needing to even open the enclosure, which is interesting, right, from a practical aspect. And again, I wanted to talk a little more about where these attacks can be found in practical life, right? And the other interesting thing, so Trezor is open source, which is really nice from a security validation perspective, because you can look through the code and sort of find issues even without doing really advanced attacks. And this was a really good example of that, a good example of where open source makes this sort of validation a lot easier, right? Because if you looked at the flash layout, right, you had the bootloader code up here, and you had this metadata area up here. So this metadata area had the recovery seed stored in it because the device needed to know the recovery seed. And it was just stored. So there's a wallet.fail talk that basically found, hey, this was just actually stored as string. So it's really easy to detect it. There's this other code sort of ahead of it, right? So if you look at the addressing here, right? So this is a lower address than here, right? So if we could read past an array located in the bootloader, it's just going to read through everything, right? So we read from the bootloader and we just keep reading, we're going to get that secret data. So what was interesting is looking at using fault injection to do that magic read, basically, right? And the fault injection we're going to look at is the fact that in this bootloader code, there's some USB descriptors. So USB descriptors, the very super fast description of the descriptors is that you have some way of telling the computer what the heck I just plugged into this computer, right? So you can see there's stuff like, vendor ID, product ID, But you also have like strings, right? So there's a string that says, hey, this is a USB 2.0 hub. And you also have stuff like the endpoints, right? So this is how the device is going to talk to it and things like that. So we have a few different sort of, configuration blocks that are getting sent from the device up to the computer. And then the computer knows what you've plugged in, how to talk to it, what driver to load, anything like that. One of these descriptors, basically, so when you get a descriptor, the computer says, hey, please send me, whatever descriptor I want. And there's some information the host, the computer that is, sends down to the device. Of importance, part of it is this W length field. So this W length field is the device saying, hey, please return up to, whatever, 100 bytes, 500 bytes, 1,000 bytes. And so the idea is that the computer can tell the device, I expect up to 1,024, or however many bytes it's capable of handling. And the device will send up to that level of data. And the idea is the computer can request, at the beginning, you don't want like a bad USB device that has these massive strings to, I guess, waste the time. And, USB spec was designed quite a while ago when there was concerns over memory usage and the initial speed was pretty slow and stuff. So you had some stuff like that, right? That the host is only going to ask for maybe the first little bit of the descriptor to figure out if it even wants to request the rest of it, right? So it can request the first 16 bytes and later request everything if it decides like, yes, okay, I need the full string. I need the full serial number. So this idea was in the USB spec, so everybody has to implement it, right, to be a legitimate USB device. And what this means is that somewhere in basically every USB stack is this call. And this call so this is a bunch of stuff saying for one specific descriptor, right? So it's checking the type, it's checking this index property to figure out, is this the right descriptor that I want to request? So this is the device code, by the way. Sorry. So this is the code running on your device. And it actually has the, here you go. So here's the minimum of a length so one of these is like the length of the sent data. One of them is the length of the W length, from the USB packet. One of them is the length of the data stored on the device. And it's just sending back whichever is shorter, right? So if the host requested less data than I have to send, less data than I have, then I'm just going to send back, however much data I actually have, or however much data the host requested. So whichever is the shorter of these two, I'm going to send back that much data. Makes sense, right? If the host requests 10,000 bytes and this descriptor's 100 bytes, I'm not going to send back 10,000. So where this gets interesting for fault injection is if we look back at everything I just showed you, right? So that quick little assembly code example, we have, again, a pretty minimal. So there's this time it's a lot more detailed, but there's still only a few instructions that matter, right? So you can see there's a compare of R1 to this fixed value of hex 9.2. We also have like some actual action on the comparison, right? And what this means is that if you compare R1 to the hex value of 9.2, it's either going to overwrite R1 with 9.2 if R1 is larger, or it's going to skip that. So if R1 is smaller, it's not going to execute this, and it's going to use whatever the value is in R1. Otherwise, it's going to use this fix. So in this case, the compiler figured out, hey, this data I'm sending back has a fixed length of hex 9.2. So you can imagine that if you never executed this instruction, or the comparison was done incorrectly, or anything in here really, what's going to happen is that this value of R1, which is how much data to send back, came from the host, right? And the host is the one that controls how much data it requests. So all of a sudden, if that code doesn't execute correctly, we have a way that the host computer can request this up to, this FF. So it's a 16-bit field, so it can request 65K of data from the device. So it's open source. So this is the cool thing. This is a game where I want to say, like, if you start playing with this stuff, there's a lot you can do, especially if you're looking at open source projects, without even necessarily digging into fault injection, just as part of, reverse engineering, looking at devices. You can find these types of interesting areas. Or, right, even if it's not open source, if you had access to the binary to reverse engineer it, you could see these comparisons. So you could kind of do a lot of this work without having to do necessarily the fault injection hardware if you're interested. So in this case, what I did is I basically took the firmware and I just removed this call, right? So even if you only had a binary, you could just remove this call, right? And all of a sudden it should accept whatever the host sent. And that's how we're going to simulate our fault injection as step one. And what you can see is that this is indeed the case. I simulate the fault injection and it sends back. So if I request 65K of data, it does send back 65K of data. And the beginning part of it's the same. What you don't see is later on, it just continues to read from memory and it returns all of the private key and stuff. And you can see, so in this case, this is like a dump of my memory, and somewhere down in here, there's these strings for whatever this wallet was that I didn't actually store anything on. So you can't try to steal it, don't worry. But that, that's pretty cool. So that's how you could validate this will work. Actually executing it is more, it's a challenging problem, but it's more an engineering problem, let's say. So it's a problem of getting all the pieces to fit together, to trigger, to time and stuff like that. So you can see this sort of holder here has a bootloader force. So if you hold down the two buttons, it always goes into bootloader mode. And we want bootloader mode because if you remember back here, right, only the bootloader code right there has the USB stack ahead of the data, because we're going to start at something and just read past it. If you try to run from the application code, it's less interesting because it's just going to read further into the application code. So that's the reason we do the bootloader mode. The EMFI tool, so this is basically a tip that's kind of positioned over the IC. And we have some way to trigger it. So at the time I'm using a Total Phase Beagle 480. And this basically is a hardware trigger on physical layer packets. So I'm triggering on physically, if you were to look at the USB wire, what you can see is this sequence of data. This data packet here, sorry. So there's basically like some data that says, hey, I'm going to request the that descriptor, and I'm going to trigger on, so in this case, the C021, I'm going to trigger on that request going over the wire. And this is assumed to be pretty well synchronized with the target device. In reality, there's a lot of jitter, so it actually takes quite some time to hit just that right point, because you can imagine if we look at this code, right, it has to hit that exact point. Right? If it doesn't hit those few instructions, it's not going to work. So in practice, I basically trigger from the USB packet and say, just keep trying until it works. So, and that basically, with doing this, it will return all of the data. So there's some longer talks that go through the details of this in a paper also on that. Now, that same thing we can actually apply to other interesting devices. So, I was really lucky to be invited here in part because of these really cool devices that are these open source authentication tokens. So you probably know of the closed source ones where you can't really inspect it. So these are pretty interesting again because you can inspect what it's actually running and you can validate, is this an issue? They can fix it and things like that. So the nice side of trusting open source for security is having this type of validation, not having to hope that the closed source version patch this or never had the bug or whatever it was, right? We have some way to test this. Really quickly, the way these things work. So you have the authentication token, right? So I have one here that we'll pull over in a second. And you basically have a public-private key pair in the token. The website or app then can store, so you once have to register the token with the website. It says, okay, here's the public key of that token. In the future, the website can send a challenge that the device signs and then sends back to the website. So if you can recover that private key, you can basically be that person. So the question is, could you recover the private key, you know, with just some access to it? And again, from a physical standpoint, it's useful if you can pick the device up, perform the attack, and put it back without having damaged it. Because if someone loses it, right, they're going to go through and say, oh crap, let's deregister this from all the websites if they hopefully wrote down or remember where they registered it. And then it's, you know, it's no use to you to clone it anymore. So there's some sort of practical, like, we need to clone this within a reasonable amount of time. You know, and people often say, like, if you can do it in a few hours, that's pretty reasonable because someone puts this in their desk or whatever it might be, right? Like, it's most people will not notice a few hour disappearance. If it's gone for, you know, a day, that starts to get a little questionable. You know, maybe you can claim they're on vacation or something like that. But there's some reasonableness to it that we want to see. Yeah, then they can verify it. And so these tokens, you know, have become pretty popular in general. So this was actually a few years ago. I pulled this. So, you know, Microsoft is saying, like, they don't use passwords, use some various authentication tokens because it's a more secure way rather than relying on user passwords only. So at the time, so this has all been fixed, of course. But at the time, basically, it was a very similar situation. So, and again, you can look at this through just the open source code even. You can look at the address that this thing is running at. So here's the address of the HID descriptor in this case, right? And then at some point later here, we have, in fact, the ECC private key, right? So this is kind of the goal that we want to get out of this. And in a similar way, we have a call to min, right, that's doing this. So there actually isn't, it's almost the same attack, different, you know, USB descriptor we're going to request, but same sort of idea. And the other sort of interesting thing, right, is that here it's like, okay, I knew where the ECC private key was, but this is actually not a big issue because if we have a public key of a device, right, we can figure out, we can really quickly brute force in memory. If we say somewhere here there's an ECC private key, you can basically just slide along and see if any of the bytes of memory, because it looks like all random data effectively, if the bytes of memory match that public key that I know. And we can do that if we have the token, because you can register a new site with the token really easily. It's going to give out the public key, right, for the new site you registered. You could do this attack to get a memory dump and then say, in that memory dump, is there a matching private key? You now know the memory layout, assuming it's not randomized each time or something, which, you know, for a really small device like this is pretty unlikely. And at the time, again, I'm talking all about before any of this was fixed. You know, this was relatively straightforward to do like that. So another example, and the final example of the sort of the practical side of pull-up, is an automotive ECU. So this is different, you know, slightly different objective here. You're not trying to necessarily steal a private key or something. This is often the case where people want to do some tuning. They want to take their ECU and modify it for, you know, various performance improvements and things like that. And so what we have here is we have a microcontroller, right? And you want to get read-write access to that microcontroller. So for various reasons, you know, tuners have been progressively locked out. Part of it is stuff like warranty return, but there's actually some new environmental regulations and cybersecurity regulations, you know, that start to more seriously mean companies actually have to prevent access or have a fair amount of resources that stop access to the ECUs to prevent people from modifying them. So in this case, the security of the ECU is really the security of this chip and this design. So in this design, there's one chip that kind of controls everything. There's no separate secure, you know, security IC or anything like that. So if you have access to this device, you kind of have everything. And so I looked a little bit at this specific device and what the security on this specific device is. So this specific device had a bootloader mode. And in the bootloader mode, you basically have this serial bootloader. So we want to get to the serial bootloader. That's the goal. And this serial bootloader is configured from external pins. So these external pins basically tell the device which way to boot. And these pins are just like, if we go back here, there's some test points on the board over here. And one of these test points is basically a pin that you can pull low and it'll enter this serial bootloader mode. Now the serial bootloader mode, right, is very well known on these, and it has a password. So you send the device a password. If the password is correct, so it's an 8-byte password, if the password is correct, it's then going to allow you to download code that you can run. So you basically need to build a bootloader that's going to run in RAM in the device and then give you access to the flash memory. Before you can do that, though, you need the correct password for the device. Every device has a unique password, so it's not even enough to recover one and then just apply it to all. So you need a way to reasonably attack these with some sort of method. So in this case, I'm looking at fault injection. And basically, the gist of it is that there's two passwords you can use. So there's a public password, which means that the flash state is disabled. So the device does not allow access to flash, but would allow access to SRAM. In the other mode, and this is what most people were using, it has this unique flash password, and the flash is enabled. So that's what we want, because we want to be able to read write flash. If you're doing some modifications to the device, that's what you'd want to have access to. And to do this, so I'm also going to pull in a little bit about power analysis. So this talk isn't really about power analysis, but there's a lot of resources I've put out there before. And so in this example, what I have is I have the same chip that's on that ECU. So this NXP chip, there's a little resistor in line in the board here, right? And so this resistor is going to allow me to observe the power, because if you have a microcontroller, right? So I have a microcontroller here, I have a resistor, VCC and ground. This is kind of what this board represents, right? And why this works is that as the current across the resistor changes, that generates, so the voltage across the resistor is the current times the resistance. So we get a changing voltage, we can monitor that and get these power traces. So yeah, this is sort of what it looks like here. So the difference here is a incorrect and correct password are in red and green respectively. And so what I want to point out is that at this early stage, right, these traces overlap. Let me make this color different. These traces overlap, right? There's a point in time where they differ. And so this is cool because, and you can see this difference here, right? This is really cool because in fact, what you're seeing is the device, possibly doing the password comparison, but then executing different code. And you can even see here, right, this sort of red small trace looks like maybe it's just going into an infinite loop, because there's a very consistent power consumption. It's clearly just doing the same operation, right? Compared to like all of this stuff, you can see the green looks very different, right? Like maybe, I think it's preparing for download of the code. Maybe it's setting up some registers, stuff like that. So we can actually see that there is a difference in how the code is executed. So the other thing I want to point out, right, is that I talked about cases where you had the ability to reverse engineer the code to figure it out. So this is an example of, even if you didn't have that, you can still find a lot about the device by observing the difference between the code paths. So if you try to boot a fake image versus a real image, or send a wrong versus correct password, right, there's a lot of stuff you can observe that's going to tell you information about how it's executing. In this case, I tested on a bunch of different devices. So one of the things I wanted to show is, if you're testing on dev boards, it's actually pretty close to testing on real ECUs. So, and I pushed it a little further. So this talk was at SCAR, so there's paper and slides and stuff up on my website if you're curious. This was an example of like how far could you push it in practicality terms. So in this case, I have my EMFI tool, right? And what I have is also like a little Arduino that's basically running the attack. So before I was running this through a Python script, but there was nothing super special about it that meant you had to use these tools. So I was using some my ChipWhisperer to do some of the timing, which was a convenience. I kind of also wanted to show, fundamentally, there's not a ton of complexity here in the actual attacks. Yeah, so that's kind of the main talk here. So my point is to show you that fault injection, it's a real thing. And we can do it on devices with a fairly minimal amount of modifications. The tool, so I'm showing demos with, my own tooling that could be fairly expensive to get, but there's a lot of other options out there. And what I want to show you, we'll have some time for questions. So if there's a lot of them, I can stop now, but I also had let me switch my camera here. What I had is I had a few little demos here. So give me 1 second. I just need to switch. Okay. I'm just going to do it in my actual camera shot here. So hopefully you can see this. Let's see if this works. Okay. So this is an example, right? So this is like an EMFI tooling. And right, all I'm going to do is run this device in sort of a manual mode. So right, if I press this button, it inserts faults. And if you want to show yourself that it's possible, rather than starting with really crazy attacks, what I have here is a little board that is running a loop. And so you can see if it resets, that red LED comes on here. When it's running, it's blinking normally. And there's another LED that indicates the loop. It's basically running some loops and seeing if you can break out of the loops, right? And it blinks an LED if I do. So if you bring an EMFI tool over top of it, you'll sort of see, you can see it rebooting quite a bit, right? And if you get the right spot, which I might not actually do here, it's always a bit of, you really would be scanning this normally, right? So you can see a lot of resets, but you might be able to get something working, pretty easily with something like that. So that's cool because, and this is open source. You can get the code. I mean, it's just some loops. There's nothing too crazy about it. You can start with really basic stuff before you get into the more advanced attack. So just because I'm kind of showing, some, am I back?
Oh, yes, okay. You're back.
Yeah, I think I switched audio instead of video. Yeah, so yeah, I wanted to show, as I was just saying at the end, there's a lot of fun you can have with this. So I think with that, if there's questions, we have a few minutes left. So
yes, so thank you for this great talk. And we have a few questions from the chat, and then the video is a bit late on YouTube, like 1 minute delay. So maybe some other questions will pop up later. So I'll start asking these ones. So Gabriele asks, what kind of environment do you suggest for this type of research? I see you're using Windows here, but any suggestions about operating system, tools, or software?
Yeah, so I'm a terrible hardware hacker because I do everything on Windows. So I use something called Jupyter for a lot of the research, which so as part of the ChipWhisperer, and we've actually been pushing, if you haven't looked at ChipWhisperer in a while, we've been putting a bunch more demos out there. It runs, so it's like an interactive Python. So if we have to run chips, and so I can install ChipWhisperer, and I can install this on Mac or anything. It's basically running Python in here. The nice thing about it, let me run this. Where's the courses? Oh, this is an old one. The nice thing about it, so I'll just show you in here, is it basically lets you run a lot of scripting that's interactive that also has plotting and stuff in it. So if you wanted to try different glitch measurements, right, you can try a bunch of different glitches, record your results, and sort of plot it all in one thing. If you're familiar with Python, it's really easy. Even if you're not, it's pretty straightforward to do that. In terms of the actual, the rest of the work, I don't think it's too critical what environment you're using. The only other major thing you might need is standard debug tools. So whatever you're more comfortable with. I'm using like Ozone, which is a Seger debugger that works on sort of everything. But if you're more GDB, that would be great too.
Okay, thank you. And another question is, how is it possible for an electromagnetic pulse to exactly change the result of an instruction? And how can it affect the execution so precisely?
So this is like a slightly open research area. There's a lot of different, to be honest, there is some different theories about it. What you really see is that so in all the digital devices, at some point you basically have a register that normally has some like either setup and hold requirements. So the clock in the clock coming in has to arrive at a certain point relative to data coming in. So if you imagine, if you're loading an instruction from a bus onto the device, what you might see, let me just use this, is if you have like data here, so if I call this data, call this clock, right? What should happen is the clock arrives and the data was stable for some time before that. If this is wrong, so if the clock arrived like right at this edge here, what you're going to find out, so ignore this one, is that now what gets latched in isn't very reliable. So this is assumed to be part of what can happen. And why this happens is that when you insert the electromagnetic fault in the system, right, you're actually doing something a little closer to voltage glitching. So if we look at like the voltage of the system, it should be very stable. If you have a big like ring on it at some point in time, this is actually going to introduce timing differences, and sort of as the ringing goes through the chip structure itself, the location of these peaks and valleys won't be consistent. So you may have sort of within the chip like timing differences on different nets at different portions. So it's almost surprising how well it can work. It's assumed, and I say assumed because it's hard to actually know exactly what's happening on the die, that's the method.
Okay, thank you. We have two more questions. One is very fast, and it is, what is an estimation of the cost for this type of research?
So it can vary. So if it's like DIY, I'd say maybe $500 by the time you build it all. The chip shader itself that I'm showing here is $3,300 US. And you can go much higher if you want, right? If you want an XY table and stuff like that. But some of the links I had to the open source ones are pretty low cost to build, like under $500, and you could do quite a bit of this.
Okay, last question is, when would you pick an electromagnetic fault injection attack over a voltage glitch attack?
So EMFI, basically, there's two reasons. Number one can be if you have the case, so like the Trezor example, where you wanted to do it through the enclosure because it's fundamental to the attack being successful that you don't want to modify the device. In the second reason, so for the example of the ECU, right, it didn't matter. I had to open the ECU anyway. That's not a consideration here. So the reason you might choose EMFI there could be that you don't want to solder to the board or something like that. More likely, EMFI has some ability to differentiate on sort of X and Y. So you can see I've sort of positioned this with just a vise over the chip. But you can also use like a table to scan it, because different areas of the die will actually have different effects. And if you especially if you start to get in devices that are like multi-core, they have a secure boot where there's a separate core that brings up the device. You may actually want to concentrate your glitch effect on one portion of the chip, right? Even without multi-core, you typically will need to concentrate with EMFI. So there might be things that you can do with EMFI that voltage glitching is going to be more difficult, but we've seen voltage glitching work on quite a few different interesting devices lately, so I wouldn't discount it.